Alright, so what we're going to talk about today is what you do when you're trying to integrate over a region that's not a rectangle, besides put it inside your favorite numerical integrator, which is the actual answer to the question in a lot of cases. But the way of thinking about what we're doing here is more important than the actual calculation. So I want you to imagine, or last time what we talked about was that so the 15.1 idea was that if you had a surface sitting over the top of a rectangle, there was a really easy way to calculate it. You could do it as an iterated integral. So if you had some rectangle down in the domain, bounded by, say, x is equal to a, x is equal to b, and then over here y is equal to c and y is equal to d, and the surface was sitting up here, this, you can imagine that you've got this sort of figure here sitting over the top of it. The volume of that figure could be calculated with an iterated integral. So the volume is equal to the double integral over the rectangle R of f of x and y dA. But if I wanted to calculate it, I could calculate that as the integral from c to d, a to b of f of x and y, where first I integrate with respect to x and then with y. Or I could do it the other way, a to b, c to d, f of xy, dy dx. So the whole upshot of 15.1 is you can calculate volume in terms of these things called iterated integrals. You can sleep them. So the question we're going to try to grapple with today is, what if the region on the bottom isn't a rectangle? Here the idea was you had some coordinate system, and there's a rectangle sitting inside of it. There's A, there's B, there's C, there's D. If I give you a different setup where there's not a rectangle in the bottom, I can certainly get more interesting figures to think about. So imagine instead we have a domain D where the x values are stuck between 0 and 2, and the y values are stuck between the function x squared and 0. So that is to say, I have now a region that looks like this. So there's 0, there's 2, and I'm integrating a surface over a region that looks like that. And I'm going to give you a really easy surface to think about here because it's easy for me to draw, which is the surface that we're going to look at is f of x and y is just equal to x. So the way of thinking about that is, if I was the surface sitting over the top of this is a sheet of paper that starts at 0 and then comes up this way. So there's like kind of this wedge shape here, but that wedge has a curved edge on it. So it's not sitting over a rectangle. If I try to draw that thing, it would look something like this. So we would go from that point to this point out here. I should exaggerate this more so it's easier to see what's happening. That's not a parabola. Wait, what am I doing? Starts at 0. Okay, from 0, 0 to 2, 4 would look something like this. And so the region that we're looking at, that region, if I wrote it in the plane, would be the sort of like parabolic looking bit like this. I'm going to reorient this so that we can see what the shape would look like. So I'm going to look at this from the other perspective, which would be if I have the parabolic region that looks in this direction, and then I drew the surface, z is equal to x, coming out the top of it, it would look something like this, where you would have these edges would be here. They would be in the background. And then there would be sort of this parabolic edge that came up to the top like this. So kind of like a door stopper would be a way of thinking about it. It's a pretty weird looking loaf of bread, but you know. And the idea is I could still write down a notion of volume for this. I could write an expression that says what the volume of that figure happens to be. That's what the double integral represents. The volume of that figure is still the double integral over the domain D of the function f of x and y dA. It still is that. I can still think about decomposing this into pieces and adding up their volumes. So So if this was a loaf of bread cut into weird slices, I guess it's like half of a croissant, right? This is the way of thinking about it. Those pieces that you were adding up would look something like this, right? You could still cut this thing up into slices and cut it and add all those volumes up. And you should still have the idea that if you did that process, if you could calculate the volume of each slice and then add up all the slice volumes, you would get the volume of the whole figure. The problem now is that the volume of those slices changes as you move around in the function. Every value every place that you put that slice, its volume is different. So it's a variable area that you're working with now. So what we're going to try to do is come up with a way of looking at how to compute that volume with something like an iterated integral. It's not going to work anymore that we can just stick some numbers in here and immediately assume that this works. Instead, what we're going to do is we're going to try to say, all right, if I'm going to do this sort of decomposition of the figure into pieces that I'm cutting in this way, how can I write that down in a kind of a calculus mindset? So when I talk about the calculus mindset, what I mean is this idea of cutting things into understandable pieces and then adding them all up to get the total. That is what calculus is about. Hand performing integrals is less important than thinking about how to actually take a complex figure like this and cut it up into pieces that are understandable. And this goes all the way back to Archimedes, right, who basically invented the basics of calculus thousands of years ago. So if I was going to try to write this integral down, I might think to myself, I need somehow to calculate the volume of this slice. Because if I could, if I could figure out the volume of the slice, I could add all the slices up. So the first thing I'll observe in the picture that I've drawn here is I'm thinking about this right now as that slice is located at a position x. And that x value is somewhere between 0 and 2. And the bottom of that slice runs from this function, which is y equals 0, up to this function, which is y equals x squared. How wide is the slice? Like this little slice right here, if I was going to think about its width. So that bread slice right there has that blue rectangle at the bottom. How wide is, what's this dimension of it?
dx.
Dx, right? It's a little skinny in the x direction. Okay, so this would be like dxy. And I'm using notation here and using dx instead of delta x, but I'm trying to convey the intuition of what's happening. Now, since I know that the depth of this thing is dx, if I could calculate the area of this face right here, I could multiply the two together. The volume of that figure would be the sort of face area times dx. That would be the volume of that slice, right? Okay, so if I could write this as a times dx, I would have the volume of the slice. Of course, sitting over the top of that is the surface. This bit right here, that part lives in the surface. The particular case I've drawn right here, the surface is a rectangle, so this is less interesting. I don't want to think about in general that this is going to be a flat line. I want to think about this as being dictated by a function. And that function has a fixed value of x, which means it's a function of y. So if I wanted to integrate, so okay, I actually gave the punchline away here. I'm going to produce this area by thinking about this as the area between two functions, a function on bottom and a function on top. So the way to do that is to say that is going to be the integral of the function, and then what direction am I moving? Well, if x is a fixed value, notice as you slide down that, you're moving in the y direction, right? This is a move in the y direction, and specifically, you're moving from y equals 0 across to y is equal to x squared. Each value of y, you come up to the top here. So again, the way of thinking about this slice right here is I've taken this and I've sort of tipped it this way so that it's sitting right here. The left side is at y equals 0. The right side is equal to x squared. The top of it is dictated by a function, f of x and y. So if I do this, that integral, which is impossible to read, sorry about the crappy chalk, let me rewrite it. If I think about the integral 0 to x squared of f of x and y d, this integral is going to be dy. That is a. For a fixed value of x, I have an integral in terms of y. Start here, end there. There's some function sitting over the top of it, and the area between the blue part and the function that's sitting on top is given by an integral. That's how you calculate the area underneath a curve, is with an integral. But if that integral is a, that's the area of one of these bread slices, and that means that the volume of the bread slice should be the integral from 0 to x squared of f of x and y dy times dx. The area of the face times its width is a volume. So that's the volume of one of the bread slices. If only there was a way I could add up all the bread slices to be the entire loaf. Another integral. So, if the volume of one slice is a dx, then the volume of all the slices altogether should be the integral from, okay, well, where are the slices? I just erased the picture that I was using, so let's go back over here. Okay, so this is the picture we've got right now. Here's our function. We've said, if you tell me the specific value of x, I can tell you the volume of the slice that sits over the top of it. Where are the slices located? From which x values are the slices located?
0 to 2.
0 to 2. Because remember, in the original setup here, x went from 0 to 2, and y went from 0 to x squared. So if I want to add up all the slices, I got to tell you where they are. The volume of each slice depends on which value of x you choose. So the total volume here is going to be, let the x values run from 0 to 2. Then you have your area integral for the face, or the volume integral for each slice, which was the integral from 0 to x squared of f of x and y dy. And then I better integrate that dx. Actually, I got this backwards, right? No, that's right. That's right. And so essentially, what this boils down to is a very nuts and bolts approach to the idea, in the same way that we could calculate an integral over a rectangle with an iterated integral. I can do the same thing on more complicated regions as long as certain conditions are met. So we calculated the volume by turning it into an iterated integral. Now I got a philosophical question, which is, should it matter what direction I slice the loaf of bread when I'm adding up the volume? If I cut it this way into yellow slices that like chop, 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 chop this way, and I add up all those volumes, I get the volume of the figure, right? That is the core idea of integral calculus. What if I cut the other way? What if I decided that I was going to be a contrarian and I was going to cut my bread the other way?
Then you'd have to do a dx integral first, and then
You would have to completely refigure this thing, right? Because now you're going to be doing an integral. Now you're fixing a y variable, a y first, and cutting the slices the other way. But the volume should still work. The basic idea of decomposing this into slices and then adding up the volumes should still work. So I'm going to write down the theorem that says when we can actually use these as iterated integrals. And then we're going to revisit this to say, what would it look like if we had to change the way we were thinking about cutting? What would we have to do in order to do that? So that's kind of I'll write the theorem down that says that, like how to calculate those, where the idea is more important than memorizing the theorem. And then we're going to revisit this with this sort of switching argument. What if I cut the other direction? what would that look like? So on page 2, you have this picture that tells you how to turn, specifically in which cases you are allowed to turn a double integral over a more general domain into an iterated integral. And there's 2 cases. So the book calls this a type 1 integral. That's not standard terminology that you need to memorize. You just, if it shows up in the book, this is what they mean. And what they say is the following. If you have a domain where x is stuck between a and b, and y is stuck between 2 functions, the picture here looks like this. You have a function up here, which is g2 of x, and a function down here, which is g1 of x, and you have some x values that clip off the ends of the regions. Then the double integral over d of f of x and y dA is the integral from a to b of the integral from g1 of x to g2 of x of f of x and y dy dx. You know that the order of integration is first in terms of y and then in terms of x, because you should be thinking, I have some sort of strips where you fix me a value of x, and that tells me the y values I need to run through in order to calculate what the areas are, the volumes for the slices. And then the type 2 integrals, this is case 2, which the book calls type 2, says, okay, well, it's also possible that you could have a domain D where the y values are trapped between constants, and the x values are trapped between functions. So now instead of having slices cut one direction, we have slices cut the other. So in that case, that would be like a function out here and a function out here, where this is h2 of y, h1 of y, and now we have y values that cut off the top and bottom of the region. So y equals d, y equals c. So the region we're studying is here, and we're thinking about strips that run the other direction. And in this case, the double integral over the region, the volume over the region, is equal to the opposite. Integrate from c to d, integrate from h1 of y to h2 of y, f of x and y. Do dx first and then dy. For a fixed value of y, it tells you the x's that you need to run between. So you have to integrate dx first. The other way, if you need some sort of heuristic to know if you're doing this correctly, is when you do this inside integral, all of the x's in the all of the y's in the problem are going to be replaced by functions of x. And then that dx is going to get rid of it all. These are numbers we're dealing with here. So if you calculate these integrals and you get variables out the other side, you've gone wrong somewhere. Right? A double integral over a region is a volume. So the variables of integration should disappear. So in our question, and this is a fundamental part of working with integration over more complicated regions, I could ask, can I switch from one to the other? Fubini's theorem in the rectangle case says I could do the integration in whatever order I want. You've told me it should be at least obvious intuitively that it should not matter how I slice this region, right? Integrating in one variable or the other should give me the same volume. So the question is, how do I actually do it? It's not as simple as just taking the numbers and changing the order of the integrals, because we're not on a rectangle anymore. When can I change from an integral that looks like this to an integral that looks like that? And so the easiest way to get into that idea is to just show you an example. So we're going to work through this example. So cutting the other direction. I started with this. And the region that we were looking at, we were thinking about the slices running this way. We went from the function y equals 0 up to the function y equals x squared. We had x is equal to 0 out to x is equal to 2. And that very clearly puts us in this case. There's a top function and a bottom function and constant values of x that we go between. If I want to switch the order of integration, I need to rebuild the way I'm describing this region with respect to the other variable. I can't have a function like going from y equals 0 to y equals x squared. I need x is equal to a function of y on the left and x is equal to a function of y on the right. That is to say, I need to draw exactly the same region, but now I need x is a function of y and a different x as a function of y, and I'm going to need some y values. I need to know y is equal to c up to y is equal to d. So I need to resolve the equation by flipping the variables. How the heck am I going to do that? Here now I'm thinking about I want my pieces to run this direction. So from left to right instead of bottom to top. Well, I know y is equal to x squared. Is there a way I could rewrite my left function as x is a function of y? It's the same function.
Square root.
Oh God, yep, there we go. Okay. So yeah, you basically invert the function where it's invertible. So if I rewrote this y equals x squared where x is a function of y, I would have x is equal to the square root of y. On the domain that we're looking at here, that inverse is defined. And I can do that. So the left function that I start at is x is equal to the square root of y. And then I start at that function and I go to the right until I hit which function? X is equal to 2. So each particular slice goes on the left hand from root y to 2 on the right. And now I have to locate where those slices actually live. Each individual slice goes from root y to 2. That is, x goes from root y to 2. Where are the slices located? Well, I start here, and I cut and cut and cut and cut until I get here. What are those y values?
0 to 4.
0 to 4.
Yeah. So that region that we've described with this different set of inequalities is the same region. This region was y is between x squared and 0, x is between 2 and 0. This is an identical region with two different descriptions. And what that says is, well, now that I've set this up correctly, this theorem says that that volume integral is equal to this iterated integral instead. So ultimately, we've got now the statement that we were trying to compute the integral over the domain of f of x and y dA. On the one hand, we've already argued that this is the integral from 0 to 2 of the integral to x squared of f of x and y dy dx. But the theorem says that I could just as well have computed the volume cutting the other direction as the integral from 0 to 4 of the integral from root y to 2 of f of x and y dx dy. This is the subtlety we have to be careful about. I can switch the order of integration as long as I'm both a type 1 and type 2 region, but when I do it, the limits of integration change. This is the single most common error that students make when they're learning this stuff, is you switch the order of integration without changing the limits. Okay. So let me just do an example of computing this, and we'll just verify that we get the same thing out each way. And then we'll talk about some more complicated cases, like the math professor's favorite exercise in this section generally. Okay. So the integral from 0 to 2 of the integral from 0 to x squared of x dy dx. Remember that way back at the beginning, the surface that we were integrating was f of x and y is equal to x, right? So the specific surface we were integrating was this plane. So that is the integral from 0 to 2. Okay, so it's the integral with respect to y. So I get xy evaluated from y is equal to 0 to y is equal to x squared dx. This is the result of performing that integral. And I'm just putting all the extra symbols in there to make sure that I remember I've integrated with respect to the right thing. After you do that substitution, you get the integral from 0 to 2 of, okay, x to the third minus 0 dx, which is x to the fourth over 4 evaluated from 0 to 2, which is 4. Now, if I've done my math correctly, and calculus still works, it should be the case that if I integrate from 0 to 4, integral from root y to 2 of x dx dy, I should get the same number. So this is an x integral this time, 0 to 4, x squared over 2 evaluated from x is equal to root y to x is equal to 2. Which gets me the integral from 0 to 4 of 2 minus 1/2 of a y. Which is equal to 2y minus 1/4 of a y squared evaluated from 0 to 4, which is 8 minus 4, which is 4. Okay, so math still works. This particular problem, there's no advantage to having gone one way or the other, right? I will say that generally people hate integrating square roots for some reason, so any time a square root shows up in a problem, you might think about switching into something involving a square instead. It's a thing that can happen. So what I'm going to do is I'm going to show you a reverse problem, and then we're going to talk about more complicated descriptions of. If I tell you what the limits are, these problems are very straightforward. If instead I say something like this, and this is like I said, the math professor's favorite sort of thing to do to ask a more complicated question is to ask a reverse question. Here's an example. Draw the region over which f is being integrated. Can the integrals be reversed? All right. So if I wrote down, say, all this chalk sucks, man. Maybe there's a better piece in here. Any white chalk? Damn. Whatever. Just keep using up my color chalk. So if I wrote down something like f of x and y is equal to x squared plus 2 plus y, and I gave you something like, actually this is on that sheet. Are there any extra copies of that floating around? Or do you guys use them all? I'm just going to use this just for a second because there's a specific problem I wanted to look at. Let's look at, okay, so it's not this function. Let's look at the integral in exercise 1.4. The integral from minus 3 to 2 of the integral from 0 to y squared of x squared plus y dx dy. Now, if all I asked you to do was to integrate that, it would be easy. You just calculate the integral and plug numbers in, right? If instead I say, draw the region you're integrating over, and then do some analysis of the region, that's more complicated. So you have to extract the inequalities that define the region from the limits of integration. When I look at this, I think, okay, the x values are stuck between x equals 0 and x is equal to y squared. The y values go between -3 and 2. So if I wanted to draw that region, okay, y squared is a function that looks like x is equal to y squared looks like this. 0 is this function. Y equals -3 is right here. Y equals 2 is right here. And the specific region that we're integrating over looks like this. Y equals -3 to y equals 2. And the way that we've set this up, this region that we've integrated over, is we're imagining that for a fixed value of y, we have values of x that are traveling between 0 and y squared, which means that the rectangles that we're thinking about run this way, right? It's a slice in this direction. Can the integrals be reversed this time? What would need to be true for the integrals to be reversed? It would need to be a type 1 region. Type 1 means the same function would have to be on the top and on the bottom, right? There'd have to be a g2 that was the top function and a g1 that was the bottom function, and that the region was between those two functions. So what's the issue here? If I started cutting this the other way, yep.
There's two different values.
There's basically two, yeah. So if we wanted to cut this the other way, it kind of is consistent up here, but if you cut all the way down for a specific value of x, there's two functions that are dictating what happens up here, and a different two functions that are happening down here. So that doesn't answer my question, though, which is, can the integrals be reversed? Is there a way I could reverse the integrals? I mean, obviously the way I've got it right now is there's a top and a bottom and another top and another bottom, and that's not going to work.
Could you switch into two different ones? So when you take the square root, you do a plus square root, and
Right.
then you do a minus square root.
So yeah, so you could actually decompose this into two regions. Because the top part up here, this function is y is equal to the square root of x. And in the bottom region, you have to work with the function y is equal to minus the square root of x. The fact that the thing you started with is not invertible means that you need to pull the function, the region you're integrating over, into two chunks if you wanted to do this. So sometimes that's worth it, sometimes it's not. In this particular case, the answer to can the integrals be reversed is yes, but there's going to be two of them, one corresponding to each piece of the region. That all by itself is a type 1 region because you have a top and a bottom. This all by itself is a type 1 region because you have a top and a bottom. So you could break it up into two pieces. Okay. Another exercise of the same flavor, of sort of an easy version of an exercise of the same flavor. Set up an integral that calculates the volume of the surface z is equal to x squared plus 2 plus y over the region bounded by y is equal to x squared and x is equal to y squared. This problem is hard because I didn't give you any inequalities at all. They've given you nothing except some sort of geometric region that you have to sketch out and figure out where the inequalities are. Over here, you had limits of integration, so you could get the inequalities. And if you had the inequalities, you could get the limits of integration. But I haven't given you nothing along those lines this time. So if I want to figure out the domain so that I can figure out what the limits of integration are, I need to draw this. Okay, so y equals x squared goes like this. And x is equal to y squared looks like this. So this question is asking us to integrate that surface over that region, the region bounded by those two curves. When you're doing an exercise like this, one of the things you have to think about is when I'm setting up the problem, the way that you decide to cut the volume up into slices dictates which type of, the way that you set this up as a type 1 or a type 2 dictates everything else. The slicing direction basically makes the formulas go in a forced way. When you look at that, any region, you should think, does it matter if I cut vertically or horizontally? Which is to say, is the same function always on top and the same function always on bottom? And or is the same function always on the left and on the right? In this particular problem, it doesn't seem to matter how we cut it. If I cut vertically, I could think about this as g1 of x and this is g2 of x, and it would be consistent for all the slices we wrote down. If I decided that I wanted to cut this direction, h1 of y would always be on the right, and h2 of y h1 of y would always be on the left, and h2 of y would always be on the right, and I could set a region up that way. So I get to pick. This is one of these where we have the luxury of choosing. Given the choice, most people seem to like to cut vertically. So what do you pick?
Let's cut the other way.
Cut the other way. Okay, so the pink slices then?
Yeah, the other way.
Okay. So if I'm going to cut with the pink slices, I need a way to describe this function as x is equal to h2 of y, and this function as x is equal to h1 of y. Well, I already have this one as x is equal to h1 of y because it's y squared. This function was the function x is equal to y squared. That's fine. That's the leftmost function. Darn! I have y is equal to x squared for the blue function, and it's not x as a function of y. If only there was something I could do.
Square root again.
Yeah, you square root it. So
X equals.
if y is equal to x squared, then x is equal to the square root of y. We're on the correct branch here because we're on the upper part. So I could think of this as being x is equal to the square root of y. So we're making some progress in describing our region with inequalities, right? Now we know that our x values are stuck between y squared and root y. Now I just need to know where the slices are. So I'm going to start here, and I'm going to cut, and as soon as I get to that spot, I stop. What y values correspond to those cuts?
Oh,
Wow, that wasn't me that time, I don't think.
not my shoe. Between 0 and 1.
Yeah, right. I mean, this is particularly, like, you could just eyeball the points of intersection here. It's not always this easy, but the y values start where the curves intersect at 0, 0, and they end at where the curves intersect at 1, 1. So our y values are between 0 and 1. So if I asked you to set up this integral and not solve it, then the answer would be the integral from 0 to 1 of the integral from y squared to the square root of y of the function x squared plus 2 plus y dx dy. This is the hardest part of these exercises typically. The integral technique itself is just something you remember, right? You've done it in the past, you know how to integrate stuff, and you just do it. But the part where you have to do some kind of analysis, the part where you think about the picture that's happening here, that's the part where like the hardest part of these exercises come from, is this move right here where I give you something abstract and you extract a function from it, or the integral from it. They can be more complicated than this, because I can force the integral to be of one type by making the function not invertible. Right, so if I used a cubic function, something to be aware of. Be aware. If I wrote down a function like y is equal to negative 2x, how do I want this to go? I want it to come down and bounce and then go through. Okay, x squared times x minus 2. So minus 2x to the third plus 4x squared, say. If you plotted that, so come down and then bounce and then go through at 0 and 2, and I ask you the question, hey, I would like you to do an integral on this region right here, you're kind of forced into a specific orientation this time. The way that I've written this down right now, you would say, okay, the x values go between 2 and 0, and the y values go between 0 and this function, right? So minus 2x to the third plus 4x squared. Can you switch the limits of integration here? In theory, yes. The volume should be the same if you cut the other direction and slice it. But I invite you to go ahead and take a run at solving for x as a function of y. Cubic functions generally are not like give themselves to nice formulations, right? Even worse, if you ran the rectangles this way, the same function would be the left and the right. So there's going to be some kind of plus or minus thing happening here, so that when you cross this point right here, all of a sudden there's going to be a negative branch and a positive branch. But even before you get to that, if you have the same function on the left and the right, seriously, go ahead and look at how you would actually have to solve this. If you've never seen, the quadratic formula that says like how you solve, if I've got a quadratic function, if I have y is equal to some ax squared plus by plus c, you could, or bx plus c, you can solve for x as a function of y here. It's got branches, but you can do it. There is a cubic function, a cubic formula, where you can solve y is equal to a cubic function of x for x, but it's awful. So be careful. Sometimes there are regions that are type 1 but not type 2, or type 2 but not type 1, right? So that you can't flip from thinking about top and bottom to left and right. Those are hard because if you get it wrong, you get the exercise wrong, basically. All right, so one more. Okay, so I'm going to give us an exercise now. So the last example. This is it's on the sheet. It is example. It's example 1.9. So the integral from 0 to 1 of the integral from root y to 1 of the square root of x cubed plus 1 dx dy. And your first thought when you see that integral is a square root of a cube? I don't know how to do that. It's not going to go by parts. There's no u substitution. This says integrate with respect to x. I've never seen something with square roots in it that's worked by parts this way. That's going to make the problem worse. Trig sub's not going to work because there's no trig identities that have cubes in them. No easy ones, anyway. So you're basically stuck. No. That's the answer is nope. You can't do it. Unless you change the order of integration. Because maybe if we could integrate with respect to y first, then something is going to show up in front of this square root, right? Because we're not going to integrate. We're going to skip integrating that and just like chuck in whatever the y makes happen, and maybe magically something like a u substitution will happen if we do it in the other direction. So do this by changing the order of integration. So how do we do that? So we're going to change order. This is the process by which we're going to do the thing where we write down the region we're interested in. Okay, so x is root y, looks like this. Then we get to x is equal to 1, which is right here. We're thinking about these things as oriented in this direction, so we're going from root y to the function 1, and then we're integrating y values from 0 to 1, which means we're going from here, 0, and then cut until we get to this point, which is 1. So it's this region that we're integrating over. From x is equal to 1, and x is equal to root y, and y is equal to 0, and y is equal to 1. And we've already done this exact example earlier. This region can be rewritten as a top function now, y is equal to x squared, so I can solve y as a function of x, a bottom function, which is y is equal to 0, and now my x values run from x equals 0 to x is equal to 1. That is the same region. But when I rethink of the region in this way, so now the inequalities are x goes from 0 to 1, and y goes from 0 to x squared, as opposed to what we started with, which is y goes from 0 to 1, and x goes from root y to 1. So we've switched the order of integration. We switched the description of the region from type 2 to type 1. And when we do that, this sort of version of Fubini's theorem that we're working with here says that integral is actually the integral from 0 to 1 of the integral from 0 to x squared of the square root of x squared plus 1. Now dy dx. I get to do a y integral first instead of an x integral. And if you do that, so you get y times the square root of x to the third plus 1 evaluated from y equals 0 to y equals x squared. You get the integral from 0 to 1 of x squared. And if you've done enough math in your life, the idea of something being done one way is impossible, but if you do the right thing, you get something that you can solve on the other side. This is like a textbook writer's dream right here, right? Or classic exercise in this class on exams as well. I tell you, hey, solve this integral. In an easy class, I'd say solve the integral by changing the order of integration. In a more difficult class, you would say solve this integral, and you're supposed to identify. I got no way to do that. So this would be done with a u sub, where you let u equal x to the third plus 1 because you made the du right there. And this idea that we can change variables like this, change the way we're thinking of the region and take an impossible integral and turn it into an easy one, that is kind of fundamental idea. Another change of variables that we're going to look at later on in the chapter is another way to do this, where instead of thinking of a region in terms of x and y, is I could instead think about a region in polar coordinates instead. Don't give me that face.
Oh, I don't want to go back.
Look, why? You can't escape polar coordinates. Like, circles exist. So I can give you a quick motivation for why you might want to do that. Suppose I told you to integrate something over a circle. So now you've got, say, -1 to 1, and this function up here is 1 minus x squared. I don't know if I can use that in my limits of integration. From 0, an integral from -1 to 1 of an integral from 0 to the square root of 1 minus x squared of some function? Ugh. That sucks. But if instead I could say, no, another way of describing that region would be maybe we could let theta go from 0 to pi and let the radius go from 0 to 1. If we could do that, then the integral would be r is equal to 0 to r is equal to 1, and theta is equal to 0 to theta is equal to pi. Those are really easy limits of integration by comparison. We're not doing this yet, so I'm just giving you a preview. I'm giving you a preview here. And this idea of changing from square to polar coordinates is going to lead us to my favorite, dumb integral trick of all time, which is how do we calculate the integral contained under the Gaussian function? All of those z tables, we're doing statistics, and so you got to go look at the z-scores on the normal distribution table. All of that comes from this, and this can be done with a trick that looks like this. It's awesome. So anyway, that's kind of where this is going. Remember, this stuff is not on this exam. This stuff, 15.2 here, not on the test. It's due next week. It's really important. Tomorrow what we're going to do is I'm going to bring in a fake test and a bunch of problems to go with it. We can work on, you guys can chew on that stuff, and then on Monday we'll have a test. There's no quiz. No, I wouldn't give you a quiz before a test.